Hey everyone, welcome back to this channel and I hope you all are doing very well. Today we are going to take a deep dive on binary search from basics to advanced, and after completing this lecture I assured you are able to tackle any kind of question such that minimax problem or binary search onto the answer problem. You will able to tackle this type of problem in just 4 steps. And what are these 4 steps? I will explain it very soon. So without wasting any time, let's start this lecture. Okay. So first of all, what is searching? Okay. So let's say I have an array 1, 2, 9, 5, 7, 13, 15. Okay. And we have to find, let's say I have to find x equal to 7. So how can we find an element in this array? So this is the index 0, 1, 2, 3, 4, 5, 6. I just initialize an pointer from at index 0 and just iterate into this array and check if this element is my required element or not. And if it is, then I just print yes. And if after traversing into this array, and if my iterator will become equal to n, and if I am not able to find the particular element, I just print no. So what I am doing over here, at 0 index I just check if my current element is x or not. If not, then I just proceed further and further and further and further, and if I am able to find out, then I just print yes. And if it is not, let's say, and if x is equal to 8, then I am not able to find this element, I am just proceed further and further and further, and after that when I am not able to find, I am just print no. Okay. So what is the overall time complexity for searching in this array? So the overall time complexity would be big O of n. I am just iterating from the index 0 to my last index. Okay. So if the constraint is less than equal to 10 to the power 9, then it will pass. But if the constraint is very high, let's say if n is less than equal to 10 to the power 18, then this will lead us to a TLE. Okay. So for this problem, there is a concept of binary search comes into the scenario. So for understanding the binary search, I have an example, that is finding a page into a book. Let's say I have a book with 300 pages and I have to find page number 70. Okay. So what we are doing practically in step 1, we just open a book. No matter which page is open, we just open a book. Then we have 3 cases. Either this page is equal x, either this page is greater than x, that is x is 17, and either this page is less than x. Okay, and x is 70 over here. So if I just open a book and I just find out the page number 70, then I am able to find this page, so I am happy over here. Okay. And if the page is greater than 70, that means my page 70 is the left and I am just opening the page number, let's say I am page number 90. So I can easily say that after this my right side would be greater than 90 to 300. So I just ignore the right side of the book, ignore the right side, and navigate myself to the left side of the book. Navigate to left. Okay. And if page is less than x, let's say if I'm opening a book and I just open page number, let's say 25, then I can easily say on my left side the page number are from 0 to 25. Okay. So I can easily ignore the left side of this book, ignore left side, and I just navigate myself to the right side of the book. Okay. And the algorithm of binary search is doing exactly like the same. Okay. So how can we say that if I am at page x, let's say I am page x this is 0 1 2 3 x 300. Let's say if I'm page x, how can I say that my right side would be greater than x and my left side would be less than x? How can we say that? Because page are in sorted manner. Okay, so if I am page x, then I can easily say that the right side would be greater than x, all the elements are, and the left side elements are lower than x. And this is the basic criteria for a binary search. That means for binary search, array should be sorted. Okay, now we understand the concept of binary search. So let's analyze this concept with a sorted array. Let's say I have to find x equal to 9. Okay, so first of all, without like we just doing in the book, we just open a book in random. We don't do something like this in binary search. We just check to the middle element. Okay, so what is the middle element in this array? That is 0 plus 7 divided by 2, that is 3. So we go on to the middle element, then again we have a 3 condition, either this element is equal x and here x is 9 over here. Okay, either this element is equal x, this element is greater than x, and this element is less than x. Okay, so if I am at my middle and I just find out my element is greater than x, then what I have to do? If my element is greater than x, then I can easily show that my right side is always also greater than x. So I ignore this right part. Okay, after ignoring this right part, I just have to consider this array. And what is the middle of this array? That is 0 plus 3 divided by 2, that is 3 divided by 2, and that is 1. At this time my middle element is 1, and just I just find out my current element is less than x. My current element is less than x. Then I can easily say that my left side elements are also less than x. So I again ignore this side, and after that I just consider this array. Okay, and after that I have to find the middle element. So how can we find the middle element? 3 plus 1 divided by 2, that is 4 divided by 2, that is at 2. Okay, so at last my pointer is at index 2 and I just find out my element is equal x, and I am happy over here. Okay, now overall what I am doing, let's say initially my array would be of size n. I just divide this array into the half and ignore the half, depend upon the condition. Then my size would be n by 2, and again my size would be n by 2, and so on. Okay, so what I am doing, what is the overall time complexity for this? I just divide my size by 2 and again by 2 and again by 2, then the overall time complexity would be logarithmic and the base is 2. So the overall time complexity is log n to the base 2. And now if my constraint is 10 to the power 18, then that what is the meaning of it? Log 10 to the power 18 base 2 means log 10 to the power 10 to the power 18 log base 10 to the power 2, that is equivalent to 60. And this algorithm passed the constraint and is less than equal to 10 to the power 18. So binary search is working very efficient for the higher constraint, and the algorithm of binary search is and it is pretty easy. So the next problem is, how can we identify a problem, either it is a binary search or not, and how can we tackle this type of problem? So for this there are 4 steps. So in my step 1, I just have to find out behavior of the function. Either it is a monotonous or not. Okay, so for this we always have to check if a function is rising something like this, if there is saturation but overall rising, or if it is decreases and if there is saturation but overall decreases, and This is not allowed. If there is something like this, too many maxima and minima, and this is not allowed. Okay, and this is called monotonous. So if a function is monotonous or a biotonic, that means if there is only single point of where dy by dx became 0 and dy by dx equal to 0. So if a function is monotonous or if a function is biotonic, then we can apply a binary search over here. So how can we check that? We over here we just on page we just say that the page is in sorted manner. So overall the graph of page is in strictly increasing, and also in this array the overall graph of the element is increasing starting from 2 to 150. Okay. Now if the function is monotonous or biotonic, then we can apply a binary search over here. Okay, and in my second step I just have to find my cutoff limit. So what is cutoff limit? So let's say I have an array of 2, 5, 9, 15, 2, 5, 9, 15, 17, 18, 100, 150, 17, 18, 100, 115. Okay, and I have to find let's say I have to find 18. Okay, so in my graph starting from 2 to 150, there is a point where 18 is lie and my answer is here. Okay, so I'm marking it as a 0. This is one region and this is another region. So I can say that this region, my element is less than equal to my required element. My element is less than equal to my required element, and at this region my element is greater than equal to my required element. Okay, so here over here this is my answer, and when I am at here I just have to traverse on the right side, and when I am at here I have to traverse on the left side, such that whenever I achieve my answer or not. Okay, so this is my step 2, and it will get more clear when we are going to solve the questions. Okay, and my step 3 is I have to write the code. Okay, so I have a template over here. Okay, so first of all I have to initialize my left and right pointer. Okay, we will discuss it very soon. Okay, so and after that I have make a condition if L plus 1 is less than R. Okay, and we have to find the mid part, that is the M equal to L plus R divided by 2. Okay, and after that I have a condition that is either I am at this region and I am that at this region. Okay, so for this I have my call a function, this, and the return type of this function is bool. Predicate, I call it predicate, and pass the parameter M, and depend upon the question what are the parameters. Okay, and we just have to return if this condition is satisfied, then I just ignore my left part. Okay, ignore left. Okay, and if it is fails, then I am at the other region, I just have to ignore my right part. Ignore right. Okay, and for the predicate function, I have my M, and other parameters depend upon the questions, and always check if I am at my left region I have to pass true, and if I am at right region I have to pass false. Okay, and if I'm at the left region, let's say for 2 to 100 I have 15 and I am at left region. What is the meaning of it? My element is less than x. So what I have to do, I just have to ignore the left region and just update L equal to m. This is my m and this is my L, and just increment my L to m, and I am just have to traverse from left to right. Okay, same as for the right thing. Okay, so let's analyze this algorithm, and for the last step, again step 4, I just have to find out my limits, that is the left L and R. This is my boundary condition. This is again depend upon the question. Okay, so let's analyze this 4 step with this example, and at this time let's say I have to find 100. Okay, so what is my first step? I just have to check if the function is monotonous or not. So here we can say that my element is in increasing 2, 5, 9, 15 and so on and 150. So we can say that the function is monotonous, so we can apply a binary search over here. So in my second state, I have to just find my cutoff point. Okay, so what is my cutoff point? I have to find 100. This is my, let's say I am calling it t equal to 100. I have to find 100 over here. Okay, so for this function, let's say this is 100. Okay, and before this is the region of x is less than 100, and this is the region x is greater than 100. Okay, and if I'm including this point, I can include this point at this side and or this side, depend upon either I am doing x is less than equal to 100 or x is greater than equal to 100. If I am doing this, then this B point is consider it as a B naught region, and if I am doing this, then B point is consider it as a B1 region. Okay, so I just know my cutoff limit, what are the regions, what are the 2 regions. Okay, and after that I have to write the code. So what was my template? I just initialize my left and right, and while L plus 1 is less than R, what I have to return? First of all, I have to find the middle element, that is the L plus R divided by 2, and after that what we have to do? We have to do if my predicate function, I pass my m, my array and my target element. Okay, and if it is satisfied, then I just ignore the left part, and that means I am on the left region and I have to ignore the left part, and if not, I just have to ignore my right part. Okay, and after that, let's say I am considering the left region including my answer. So my left region is x is less than equal to 100, and my right region is x is greater than 100. Okay, so after that my L is here and my R is my right region. So what is the cutoff limit of left region? That is L, and L would be my answer. And what is the cutoff limit of right? That is the first element, which is x, which is greater than my required element. Okay, so over here I am writing my predicate function, bool predicate. I pass m, array and target. Okay, and check if my array m is less than equal to target, I just have to return true, else I just have to return false. Okay, I have to return false, and after that I just have to return or print my L. Okay, so and what is my step 4? I just have to find out what is my L, what is my R. So for this array my L is at 0 and my R is at 7. I am just making it more safer. I am just initialize my L from here, that is from -1, and my R from n, that is 8. N is my 8. Okay, so let's take a dry run. Okay, initially my L is -1 and I have to find out this T. Okay, target element is 100 and my R is 8. So what is M? 8 plus, that means -1 divided by 2, 7 divided by 2, that is 3. And when I get my M, that is M is equal to 3, I just have to call a predicate function, and in predicate function I have checked if my current element is less than equal to my target element or not, and yes, it is less than my target element, then I just have to ignore my left part, and here I just return true, and in true I just ignore my left part and update my L to M. Okay, and again now my updated L is 3, my R is 8. So again my middle element would be 3 plus 7 divided by 2, that is 5. So again I find my middle element over here and just check and just call a predicate function, and in predicate function we just check if my array M is less than equal to the my target element. I just return true, and again I update my L and ignore the left part. Then again my L is 5, R is 8, and my M is 5 plus 8 divided by 2, that means 13 by 2, that means 6. Okay, at this time my M is here. After getting the index M, I just call a predicate function, and in predicate function I just check if my current element is less than equal to 2t, that is our targeted element, and if it is, then again I ignore the left part and update my L, that is L equal to M. Okay, now my L is, if I am in a graph, this is my T equal to 100, I call it B. This is my B0 region, this is my B1 region. Now my L is here, and what is this region? This is element is less than equal to X, and this region element is just greater than equal to X, and my L is at my maximum point. Okay, so again I just have to update my L equal to 6 and R equal to 8. Okay, again my M equal to 6 plus 8 divided by 2, that is 14 divided by 2, that means 7. Okay, now my M is at 7 and L is at 6 and R is at 8. So I check if this current element is greater than equal to my targeted or not. That means I have to call a predicate function. In predicate function I just check if my current element is less than equal to the targeted element, that is no, it is greater than element, then I just return the false. While returning a false, I just update my R equal to M. So here my R is equal to 7. Now my L is equal to 6, R is equal to 7. Then what we have in my while loop, I just every time we check 6 plus 1 is greater than 7, no, is equal 7. So at less than 7, no, it is equal 7. So at this time the while loop not satisfy this condition and while loop break. So what we see 6 equal to L equal to 6 and R is equal to 7, and also we can see that L is at my last index and R is my just greater than 1 unit by L. Okay, so by observing this, L is what? L is the including X or less than X. Okay, and R is always greater, R is at index which is always greater than X. So we have two boundaries separated for B0 region and B1 region, and R1 is the lowest index and L is at highest index. Okay, so after that I just have to print my, if I want my index, then I just have to print my L. Okay, now my next question is, and in the question number 2, let's say we have given an array again and we have to find maximum element which is just less than equal to 12. Okay, so again we just have to check step 1 if it is a monotonous or not. So it is a sorted, then step 1 is okay, so we can apply a binary search over here. So in step 2 we just have to set a boundary. Okay, so this is my function starting from 2 to 150. Okay, and what we have to require, we have to just check, find the maximum element which is just less than or equal to 12. Okay, so let's say if this is a 12 whenever in a graph. Okay, and what we require, we just, and this is a region is just less than equal to 12, and this is a region of greater than 12. Okay, and this is my region B0 and this is my region B1. Okay, so this is at the maximum point where this condition satisfy. Okay, so after processing all of this thing, my L would be here and my R would be just L plus 1 unit greater than L, and my R represent, and what my L represent, my L represent my array L represent this L is just less than or equal to 12 and my R represent just greater than 12. So if I have a question of this, I have to find the maximum element just less than equal to 12, then I just have to return my array L, and if I have a question I have to find minimum element just greater than 12, then I just have to return array of R. Okay, so again let's take a dry run. First of all my L would be -1 and my R would be 8. For this my L is here and my R is at 8. Okay, so initially my M is 8 minus 1 divided by 2, that is 3. Initially my M is here. What we can see that 15 is greater than equal to, where is my code, 15 is greater than equal to my target element. So I return false and I just update my R. So my R would be here, and again my L would be -1 and my R would be at 3, and again make 3 minus 1 divided by 2, that is 2 minus 2 divided by 1, that is 1. Okay, so now I am at index 1. So what we can find out, I just find out 5 is less than equal to 12. So I just have to return my predicate function, return this condition is satisfied, array M is less than equal to 2, so it passed true and it ignore left, and my L is updated to M. So at this time my L is updated to M. So at this time L is 1 and R is 3. Okay, so what is my next middle element? L plus 3 divided, 1 plus 3 divided by 2, that is 2. So at this time M is over here, and we can also see that 9 at this element is 9. My current element is less than the target. So I just have to return true, and if I am returning true, where is the array? If I am returning true, I just update my L to here. Okay, so again my L is equal to 2 and my R is equal to 3, and at this condition L plus 1 is less than R is not satisfied, and we exit out from the loop. So overall what we have, ARR2 is less than equal to 12. So what is ARR2 is 9. ARR2 is 9. Okay, and for R, ARR3 is greater than 12, and what is my ARR3 is? ARR3 is 15. So we can simply see that after setting a boundary, L is my the last index where x is less than equal to 12, and R is my first index where x is greater than 12. So I can easily find the maximum element less than equal to 12 and the minimum element less than equal to greater than equal to 12. Okay, so with the same template or code, I can find three type of problem. Either I can find the particular element, and either I can find the less than equal to the element, or either I can find to the greater than that element. Okay, so in my question 3, I have given an array. Let's say I have given 2, 3, 4, 4, 4, 5 and 6. Okay, that is 0, 1, 2, 3, 4, 5 and 6. Okay, and I have to find out for that particular element x equal to 4, I want my starting index, that is 2. I want my last index, that is 4. So how can we find out? Okay, and also if I am after finding the starting index and last index, I am also able to find how many 4s are there. Okay, so if I am reducing 4 minus 2 plus 1, that is 4 minus 2 is 2 and 2 plus 1 is 3, then I just calculate that there are 3 4 in this array. So how can we find this? So initially, starting from the beginning, in my step 1, what is my 4-step procedure? In my step 1, I just check if what is the behavior of this function. So we can simply see that 2, 3, 4, 4 and 2, then 3, then 4, then it will at saturation, then again 5, then 6. Okay, so this is a monotonous function, so I can apply a binary search over here. Okay, in my step 2, I just have to set my cutoff limit. Okay, so let's say this is my overall increasing graph. Okay, so first of all, I just have to find out the starting element. So for the starting element, what I have required, I have required at this region, let's say my x equal to 4, at this region I want my element is greater than equal to 4, and for this region I want my element is less than 4. Okay, so after that, and this is the starting index of 4, and after processing all of this all of my array, my R would be at here and my L would be at here, and the element at the L index is just less than 4, and my element at index R is equal to the 4 and greater than, if 4 is not included. So after the array, my 2, 3, 4, 4, 4, 5 and 6, after processing, my L is here and my R should be here. Okay, so this is my step 2. For my step 3, I just have to write the code. Okay, so this is going to be same as it is. So if I am just make a copy paste. Okay, so this thing is going to be same as it is, and after that I just have to write my predicate function, bool predicate. I just passed my m, my array, my t, and what I have to find, first of all I have to find my starting index. Okay, so for this, if my array m is less than t, I just have to return true, and if not, I just have to return false. Okay, this would be my predicate function, and at this time we just, for ignoring left, we just have to take a region that is my element. What is my left region? My element is less than the target element. My element is less than the target element. That means I just have to ignore left and my update left to the right side. And when I am at this region, I just have to return false and increase my r, update my r to the m, and traverse from right to the left. Okay, so let's take a dry run for 2 3 triple 4 5 6. And my index is 0 1 2 3 4 5 6. This is my -1, this is 7. So initially in my step 4 I set a limit that is L from -1 and R from 7. So what is M? 7 minus 1 divided by 2, that is 3. So over here M is at 3. So I check that my current element is equal to the target element. So I just, so this condition, so this is for only less than the target element, so this is not satisfied, so I return false. When I am returning false, I just update my r to m. So after updating, my r should be here, and again my L is -1, my r is 3. So for my middle element, 3 minus 1 divided by 2, that is 2 divided by 2, that is 1. Now again my m is here, and what I have to find out, I just have to call my predicate function and just check my current element is less than target. So I return true, and when I am returning true, I just update my L over here. When I am updating my L index to 1 index, that is L equal to 1 and R equal to 3, and again I have to find the middle element. 3 plus 1 divided by 2, that is 4 divided by 2, that is 2. Okay, now I am getting m equal to 2, so my m index is at 2, and just check my current element is equal to my target element, so I return false. When I am returning false, I just update my r over here, and after updating r, L is what? L is at 1, R is at 2. And when I am getting L equal to 1 and R equal to 2, so I can simply say that L plus 1 divided by less than equal to R is, this is not satisfied, and then I just exit out from the loop. And after that, what is my L? My array at L is less than 4, and it is satisfied. We can easily see that less than 4. Where is my L? The maximum index of L, which satisfy less than 4. And what is my R? Array R is greater than equal to 4. That is the minimum index where element is greater than equal to 4. So this is the minimum element where the elements are greater than equal to 4. So I just have to return my st equal to R. So this is my starting index, and for my last index, what I have to do, I just have to update my predicate function. This is for my last index. For my starting index, this is for my starting index. For my last index, I just have to update a simple thing. First of all, I just have to check the step 1, that is if the function is monotonous or not. Then yeah, it is the monotonous. Then step 1 is satisfied. For step 2, I just have to set the boundary condition, that is the cutoff limit. Okay, so if this is a graph, this is a function, then what is this and what is this region? So at this time my element is less than equal to 4, and at this region my elements should be greater than equal to 4. So I can easily find out, after processing the array, I can easily find out what would be my L. My L is the last index which satisfy the element is less than equal to 4. And what is my R? R is my the element at that index r is the element which is just greater than equal to 4. Okay, so and what we have required, the last element which satisfy the element is equal to 4. Okay, so I just have to update my predicate function, predicate m array and target. Okay, and if my array m is what, just less than equal to my target element, I just have to return true, or I just have to return false. Okay, now again let's take a dry run with 2, 3, 4, then 5 and 6, 0, 1, 2, 3, 4, 5 and 6. And -1 and 7. So initially my L is here and my R is here. Okay, so what is my middle element? 7 minus 1 divided by 2, that is the 6 divided by 2, that is the 3, and my M is here. So I can see that my current element is equal to the target element, so I return true. When I am returning true, I just update my R, that will be my L is over equal to 3. So after updating my L equal to 3 and R is equal to 7, then again M is equal to 7 plus 3 divided by 2, that is 5. Okay, so in my second step my M is equal to 5, and then I check that this element is greater than the target element, so I return false. When I am returning a false, I just update R to M. So L equal to 3, R equal to 5. Again the middle element would be 5 plus 3 divided by 2, that is 4, and at this time my M is at 4, and we see that my current element is equal to the target element, so I return true. That means I just update my L equal to M. Okay, while updating my L equal to 4, my R equal to 5, then I just am at my cutoff limit. Okay, that means I am at my cutoff limit. This is my L, this is my R, and this is the region where the element is greater than equal to 4, sorry, less than equal to 4. That means this is the last index where x is equal 4 or x is less than equal to 4, and this is the first index, R is the first index where x is greater than 4. So for this I just have to return my last index as a L. Okay, so here I can find out my last index, I can find out my starting index, so I can easily find out my how many 4 are there in the array by take a difference of last index minus first index plus 1. Okay, okay, now I have a question number 4, and this is a pretty awesome question, and the question is, I have a given n, okay, and I have to find k where such that 1 plus 2 plus 3 plus 4 such that and so on and plus k is less than equal to n. Okay, and I have to find this k. I have given this n. Now let's apply the 4th step and check if it is a problem of the binary search or not, and if it is yes, then how can we tackle this. So let's say, so what is my step 1? That is the behavior. Okay, so the behavior of the function is monotonous or not. Okay, so if k equal to 1, then sum is 1 plus 2, sorry 1 1. Okay, if k equal to 2, then sum is 1 plus 2, that is 3. Okay, and if k is equal to 3, then 1 plus 2 plus 3, that is 6. If k is equal to 4, then 1 plus 2 plus 3 plus 4, that is 10, and if k is equal to 5, then 1 plus 2 plus 3 plus 4 plus 5, that is 15. Okay, so if I increase k, my sum is also increasing, and what is n over here? That is the sum of all element from 1 to k. Okay, so if I make a graph, okay, this is my k, this is my sum. Okay, so if I increase my k, my sum is also increasing. Okay, and let's say this is my answer n. Okay, so what is this region b0 and what is this region? Okay, so this is a region where sum is less than n, and this is the region where my sum is greater than n, and at this point my sum is equal to n. So if I am including this point into the b naught region, then the what is the overall region? So this region would become sum is less than equal to n. Okay, and after processing for all k, I have my L at point n. Okay, and my R at just sum is greater than n. Okay, and just I have to return my k equal to L. Okay, so I have completed my step 1 behavior. What is the behavior? And we can say that behavior is the monotonous, that is if we increase k, the sum is increasing. I just have to check 2, that is the cutoff point, cutoff limit. We just have to find our cutoff limit. Okay, and we have our regions. Okay, in step 3 I have to write code. Okay, so I just initialize my L and R. For my step 4 I initialize my L equal to 0 and my R, let's say for now I am initializing my R equal to n. Okay, so what next? I just L plus R is less than R, then I just have to call, first of all I have to call predicate function. In predicate function, before this I have to find the middle element, m equal to L plus R divided by 2. After that I have to just pass the m. Okay, then I have to pass n. Okay, and if it is yes, then L is updated. I just ignore the left part, and if it is not else, I just ignore the right part, that is update my R. And in my predicate function, predicate function, I have m and I have n. Okay, so the first of all I have to find what is m. M is the current k. So the first of all I have to find sum. Sum is finding the n natural number, that is m into m plus 1 divided by 2. After finding the sum, I just have to check if my current sum is less than equal to n or not. If it is less than equal to n, then this is my B naught region, and I just have to update, I just have to return L for updating my L, and if it is not, I just have to return true over here and return false over here. Okay, and if it is not, I just have to update R such that my L would become at point n and my R would become just L plus 1. Okay, so let's take a dry run for n equal to 20. Okay, so my L is 0, my R is 20. So what is my middle element? So my middle element would be 20 plus 0 divided by 2, that is 10. Okay, now after finding m, I just have to call the predicate function. So the first of all I have to find the sum. What is the sum? 10 into 10 plus 1 divided by 2, that is 5, that means 5 into 11, that is 55. So we can see that 55 is greater than my n. My n is 20. So if 55 is greater than n, then I just return false. If I am returning false, then I just update my R equal to m. So my updated, my L is 0 and my updated R will become 20, sorry, what is my updated R? Will become 10. Okay, after that I let's find out the middle element, that is a 10 plus 0 divided by 2, that is the 5. Okay, now again I have to after calculating the middle, I just have to call the predicate function. In predicate function I just have to find out the current sum, that is 5 into 5 plus 1 divided by 2, 3, that means 15. So my current sum is 15. So after getting my current sum is less than equal to n, I just return true over here, and when I am returning true, I just update my L to M. Okay, so my updated L would become 5 and my R would become 10. Okay, now what is my middle part? 10 plus 5 divided by 2, that is 15 divided by 2, that means 7. Now again I have to calculate the sum for 7. 7 into 7 plus 1, 8 divided by 2, and that will become 28. So again we find out 28 is greater than 20, so we return false and we update R equal to M. So again our L is same as it is, but our R would become 7, and we just have to find M. M plus 7 divided by 2, that is 12 by 2, that would be 6. So again, what is the sum of 1 to 6? That is 6 into 7 divided by 2, and this will become 21. Okay, now again 21 is greater than 20, so again we return false and we update R. So again after updating, my L would become 5 and my R would become 6. So after that we just reach the cutoff limit point, that is R is 5 and L is 5 and R is just 1 unit greater than L. So I am at here, L is 5 and my R is 6. Okay, so after getting this, I just found my k equal to L, where the sum of 1 plus 2 plus 3 plus 4 plus 5 is less than equal to n, where n is my 20 and sum of 5 natural number will be 15. Okay, and if I find 1 plus 2 plus 3 plus 4 plus 5 plus 6, this will become 21, which is just greater than n. Okay, so here we can find our k, and this is a pretty awesome question. Okay, now let's talk about step 4. Okay, in which we have to determine the value of L and R. Okay, so if we can see, we initialize L as a 0 and R as a, what is 20 here? 20 is n. So over here we initialize L as a 0 and R as a n. Okay, so the every time what is the lowest value of k? That is 1. Okay, so for taking a safer case, I just decrement this 1 by 1 unit. So I take, just for safer case, I just make L equal to 0, so that the minimum value of k is in our range. Okay, and what with the value of R? Currently I suppose it is n. So what is n over here? What is n? The sum of all natural number till k. This is our n. Okay, so we can see that if k is not equal to 1, then k is always going to the less than n. So assuming R as a n is not appropriate. Okay, so what is the value, what we can determine the value of R? So if we can simply see that 1 plus 2 plus dash 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 plus k, if it is less than equal to n, then we can simply say that k into k plus 1 divided by 2 is less than n. Okay, so and let's suppose k is a very large number, so k is equivalent to k plus 1. Okay, so I can simply assume that k square is less than equal to 2n. Okay, and if I am determining k, what is the k is root under 2n. Okay, so this is the largest value of k for a particular n. So for L, I just initialize it at a 0, and R I just initialize it at a root 2n plus, for making it safer, I just increment it by 1 unit. Okay, And what would be the overall time complexity? So if I'm taking r is equal to n, then our time complexity would be big O of log n to the base 2. But if but here r is not n, r is what? R is, let's say, if I am ignoring this coefficient, what is the r? Root 2 n. So the overall time complexity would be big O of root 2 n. Okay. And again, if you want to ignore this arbitrary constant, then the updated time complexity would be big O of log root n to the base 2. So this is the overall time complexity for this efficient approach. Okay. So moving to the next question, I have question number 5. In this question, I have given a number of people, that is the n people. I have given n people. Let's say these are the people, and for each people arriving time period is given. That is, for this is 1, 14, 1, 10, 3 and 4. Okay, these all are in second. So for a particular person, let's say I have n equal to 6 people. For all people, I have a given array of time period. Okay, and also I have a given of m buses. I have given a m bus. Okay, and for each bus there is a overall C capacity. C is the capacity. I have given C capacity, and it is guaranteed that m into C is always going to be greater than n. That means the availability of seat is always greater than or equal to the number of people. Okay. Now what we have to determine? We have to determine minimum of maximum waiting time of passenger. So first of all, let's analyze this question. Okay, so I have given, let's say I have m equal to 3, C equal to 2, n equal to 6, and we have, I can take it as a same 1, 14, 1, 10, 3 and 4. These are the waiting time period of 6 people. So our task is we have to place all the person into the bus and we have to calculate the waiting time. How can we do that? Let's say this is the bus number 1 and 0, 1, 2, 3, 4, 5, and I am picking the first person and placing into the bus number 1. Okay. After placing this person bus number 1, again I am placing the second person into the bus number 1. Why? The maximum capacity is 2. Okay. So the overall maximum waiting time for this person is 14 minus 1 is 13. Okay. Again, for in bus number 2, I am placing the third person into the bus number 2. Okay, and placing the fourth person in bus number 2. Again, I am calculating the maximum waiting time for this bus. What is it? 10 minus 1 is 9 seconds. Okay, and in bus 3, I am placing the fifth person into the bus number 3, and again placing the last person into the bus number 3 and calculating the maximum waiting time. That is the 4 minus 3 is 1. Okay, so what is the overall maximum waiting time in between three of it? That is the 13. So the answer for this configuration is 13. So the question is, can we get the further minimum waiting time by changing the alternation of the passenger? And the answer is yes. How? After sorting. Why we are sorting? We are just doing sorting because I want my adjacent people as the minimum as the same as the person. Okay. So after sorting, we have 1, 1, 3, 4, 10 and 14. Okay. So after sorting, what we can see that 10 is not 10 is not get make a difference with 1, 14 is not get a difference with 1. So if I am taking 14, I want the maximum waiting time from the remaining array, and yeah, it is, yes, the 10 is just adjacent to the 14. So sorting is good for making efficient waiting time. Okay, so again analyzing this pattern with the sorted manner, I have 3 buses. First of all, I am placing the first person, again the second person, and the waiting time is 0. Okay, again placing the third person and the fourth person, and the waiting time is 4 minus 3 is 1. Again the second last person and the last person, and the maximum waiting time is 3. So what is the maximum waiting time among these? That is the 3, and this is our final answer. Okay, now manually we are able to find the answer is 3. So how can we think about this is the question of binary search? So, and how can we think about the answer? So just apply the 4 step over here. What is our first step? Our first step to check the behavior of the function. Okay, so how can we check the behavior of the function? So what we have to determine? We have to determine the waiting time should be minimized. So our answer is waiting time, and I want it to the maximum waiting time over all the buses should be minimized. So waiting time is depending on what? What we have given on the variable? I have given people, I have given capacity, I have given bus. Okay, and here the people and capacity are fixed. So we can simply say that the people and capacity does not depend upon directly onto the waiting time. And what is our last option? That is number of buses. Okay, so let's say if I am increasing the number of bus, let's say m equal to 4, and let's see what happened. I have 4 buses. Okay, and at first time I just place 1 1, then 3 4, then 10, then 14. Now let's see what is the waiting time over here. 1 minus 1 is 0, 4 minus 3 is 1, 10, there is only one person in this bus, so the waiting time is 0 and again 0. So what is the maximum waiting time over here? 1. So what we can able to see over here, if I am increasing the number of bus, then maximum waiting time should get minimized. Okay, so over here we can relate this number of bus and waiting time in monotonous manner. So we can simply say that if this is the waiting time and this is the number of bus, so if we increase the number of bus, the waiting time should be minimum, and if we decrease the number of bus, then waiting time is increases. Okay, so overall this graph is decreasing and it is a monotonic function. So we can simply say that we can apply a binary search over here. Okay, now we have to check the step 2. What is the step 2? Cutoff limit. Okay, now this is waiting time, this is our number of buses, and let's say this is our graph. Okay, and at this point, let's say this is our number of bus given. Okay, so the whole region is separated by 2 parts. Let's say this is the B0 region, this is the B1 region. Okay, and at this point, this is our maximum number of bus we have to give in. Okay, now what? B0 is the region of what? Where number of buses are greater than m, and B1 is the region of number of buses is less than m. And let's say I am including this point as in the B1 region, so I am including the equal also. Okay, now B1 is the region of including this m and less than the number of buses, and B0 is the region of the number of buses is greater than. So in my approach, let's say I am talking about the step number 3, I have to write code. Okay, so for this part the code will remain same, and what I have to determine, I have to determine waiting time. Okay, so L and R would be the waiting time. So what is L and what is R? Let's talk about this. So what is the maximum waiting time for this particular example? That is the maximum minus minimum, that is 13. Okay, so always for R I have to determine, for L let's say L is equal to 0 for safer case, and R would be what it is. This is ARR n minus 1 minus ARR 0, and for making it in a range, so I just increment R by 1. Okay, now in my left side, I just, after initializing my L and R, I just have to write the while loop L plus 1 is less than R, and after that what I have to write, I just check. First of all I have to determine int m equal to L plus R divided by 2, and after that if predicate, I have to pass m array capacity number of people, that is the size of array, okay, capacity, and the number of buses also. So if I am not passing the n, I can simply pass the number of buses given. Okay, and if it is yes, then I just update L equal to m for my B0 region, and if no else I just update my R, and after that what I have to determine, I am including this m in a B1 region, so after the processing the R should be here and L should be here, so I have to return R, that is the minimum. So after processing all this while loop, I am just printing my R. Okay, and in my predicate function, I have my m, I have my array, I have my capacity, and I have my number of buses given. Okay, and let's say instead of writing this m, I am just writing it as a initializing over here as a I call it as a waiting time. Okay, so overall what I have to determine, I just have to find out for this particular waiting time how many number of buses are required. Okay, so I initialize a int required buses as a 0, and after processing for this particular waiting time how many required buses are there. Okay, and after processing I just have to check if the required buses is greater than m, the given buses. So I am in which region? If the required buses number of buses are greater than the given buses, then I am this B0 region. So I just, for B0 region, I just have to return true, then I just have to return true, else I have to return false. Okay, now, and how can we calculate the required buses? So over here I initialize, let's say I am, first of all what is my array, 1 1, after that 3 4 10 and 14. Okay, here for finding an algorithm to find the number of required buses, let's take an example and figure it out how the algorithm works. Okay, So let's take waiting time equal to 3. I have given a bus capacity that is 2. Okay, and let's I have the bus number 1, and initially the current people is 0. So I pick 0, 1, 2, 3, 4, 5. So I pick the first person and place it into the bus number 1. Okay, and after placing it, my current people is 1. Let's say I am initializing the variable current people. My current people is 1 and my overall capacity for bus is 2. So I am able to pick another person. Okay, so again I am picking another person and place into the same bus. Okay, now what is the waiting time? 1 minus 1 is 0. Okay, and while I am picking the further person, now my capacity is full, so I have to require the second bus. Okay, so again I am picking a person and just place into the second bus. Okay, and for this bus my current person is 1 and my capacity is 2. So I am able to place another person over here. Okay, so I am picking the next person and placing over here. Okay, now what is the waiting time? 4 minus 3, that is 1. Okay, so again my capacity for this, my current person, that is for this particular bus is 2, which is equal to the current capacity. So again I have to require another buses, that is the bus number 3. Okay, now what I am just picking this person and placing over to the next bus, that is 10, and after that my current person for this particular bus is 1 and capacity is 2, so I can place another person. So again I am picking this person and placing to the third bus. While I am placing to the third bus, what is the maximum time for this bus? 14 minus 10 is 4, but I have to require the waiting time is 3. So again here I am not able to place this person into the same bus. Okay, so I just have to require one more bus and place the last person into the last bus. Okay, and the waiting time for this bus is 0 and the waiting time for this bus is 0, and we can see that all waiting time is less than equal to 3. Okay, now what is the number of required buses? That is 4, and this required buses is greater than m, and what is our capital M? Is 3. I have given 3 buses. So after getting the required buses is greater than m, I just have to return true, and after returning true I just update my L to m. Okay, now we understand how the number of required buses algorithm works. So we can simply write the code for the number of required buses. How? So for the code, let's say I have 1, 1, 3, 4, after that 10 and 14. Okay, 0, 1, 2, 3, 4, 5. So for all waiting time I have to traverse from 0 to my last index. So every time I initialize an iterator from I equal to 0, I initialize a current person for that particular bus, that is 1, and last we have to initialize a pre-variable starting from ARR, the first person. Why I am initializing a pre-variable? Because every time I have to determine the waiting time with respect to the previous person, and this pre is the previous person. Okay, and after initializing this variable I start a while loop, I less than array dot size. Okay, and every time I have to check if my current person is greater than capacity, or if the array I minus pre is greater than my waiting time. I just have to increase my, again I have to initialize a required bus, that is initially I am initializing it as a 1. So whenever this happen I just update my required bus. Okay, and again I have to initialize my current people as a 1 and my pre as a ARRI. And if not, what is this condition? I just have to determine the condition whenever I have to require the buses, whenever the capacity is full, and whenever the weighting is greater than the particular weighting, which is determined by the middle of the L and R divided by 2, this weighting. Okay. So for if it is not, then I just increase my, every time whenever I am placing a person into the particular bus, I just increase this, and okay, it is fine. And every time I just increase my iterator. Okay. And after completing this loop, I have my required buses. And after that, this logic will work. I have to check required buses is greater than the given buses, then I have to return true, that is I am at B naught region, and if not, I have to return false because I am at B1 region. Okay. Now let's take a dry run for this particular. I have 1, 1, then 3, 4, 10 and 14. Initially my L is 0, my R is 14 minus 1 is 13, and for making safer I just increment it by 1. Okay. So now what is the M? 14 plus 0 divided by 2, that is 7. Okay. So initially my waiting time is 7. So first of all I have to calculate for waiting time is 7. Okay. First of all I have to calculate the required buses. How can we find that? We can simply initialize an iterator, current person as 1, pre as a ARR 0 and required buses as a 1. Okay. So in bus 1, what is my current person right now? 1. What is my PRE? That is also ARR 0. So ARR 0 is 1, current person is 1, and required buses is also 1. So when I am at this iterator, what is happening over here? I just have to check 1 minus 1. 1 minus 1 is what? 0. This is less than my waiting time. Yes. And what is my current person? That is 1. This is less than capacity. Yes. So I am able to place my first person into this bus. Okay. After that I just increase my current person and increase my iterator. So my I would become at 0, 1, 2, 3, 4, 5. My I would become 1 and my current percentage become 2. Okay. So at my current person is 2. My current person is 2, and I just have to, first of all, for checking the waiting time, again 1 minus my PRE is also 1. 1 minus 1 is 0. So this condition fail, and if we check my current person is 2 and 2 is not greater than 2, so this condition is also fail. So again I have to increase my current person and increase my iterator. So again my current person is 3, and I am also able to place this person in particular bus. Okay. And now my current person is 3 and I is also 2. Okay. I is also 2. Now the element is 3. My current person is 3, my I is at 2, and my waiting time is 7. Okay. And initially I just fill this bus 1, 1. So my current person is 3, then this satisfies this condition. Current person is greater than this condition. So I required a new bus. I just again update my current person as a 1 and PRE as a ARRI. So my current person would be updated to 1 and my PRE should be ARRI, that is PRE is 3. So I am able to place this person into the new bus. Okay. And after placing it, again I have to increment the current person. So current person is further incremented to 1 to 2, and my I is also incremented. Okay, now what? Again my current person is 2, my I is 3, okay, and my PR is 4. So first of all I have to check 4 minus 3 is 1. Okay, so 1 is less than 7, so this condition is failed. And again check current person is 2 and current person is greater than C, this is also failed. So I am able to place this person into this buses. When I am able to place this person into this bus, again I just have to increment the current person and iterator. So the current person would become 3 and my I would become 4. Okay, so at I equal to 4, what we have? First of all I have to check the current person is greater than C. Yes, and this is satisfied. My current person is 3 is greater than 2. So in this condition my required buses is increased, so I have to require one more bus. Then my current person is set to be 1 and PR is set to be ARRI. So current person is set to be 1 and my PR is set to be ARRI, that is 10. Okay, now I am able to place this person, and after that I increment my current person as 1 to 2 and increment my I to 4 to 5. Okay, now I am at my last index and check the current person 2 is not greater than 2, so this is not satisfied. So again check ARRI minus P. So what is my ARRI? 14. And what is my pre? That is the previous person. 14 minus 10 is 4, and 4 is less than 7, so this is again satisfied. So I am able to place this person into this last bus. Okay, so after exiting this loop I just have to determine what is the required number of buses, that is 1 2 3. Okay, so my required buses is 3 and my overall buses is again 3. So after that this condition is failed and this condition is satisfied, so I just return false. After getting the false condition, I just have to update my R equal to M. So what is my M? M is 7. So after this my L is 0, R is 7, and again I have to calculate M equal to 7 plus 0 divided by 2, that is 7 by 2, that is 3. Okay, again my waiting time is 3. And at this time we know how our required number of buses algorithm is work, so we can just determine so quickly without doing this a lot of calculation. Okay, so what we have 1 1 3 4 10 and 14. Okay, so I have waiting time is equal to 3. So first of all I have to place my first person, then second person. 1 minus 1 is 0, so this satisfy. Again the third person over here and the fourth person over here. 4 minus 3 is 1, this is again less than waiting time, and 10, then 14, then 14 minus 10 is 4, which is greater than 10. Then we have to require one more bus. Okay, so again the waiting time for this bus is 0 and waiting time for this bus is 0. And after exiting from while loop we have our required buses as a 4, and 4 is greater than M, and M is what? M is given as a 3. So at this time our required bus is greater than M. So at this time our required bus is greater than M. So after that I just return true, and while I am returning true I just update my L to M. Okay, so after this my L would become what? My L would become 3 and my R would become what? 7. Okay, again I have to find M. M is equal to 7 plus 3 divided by 2, that is 10 divided by 2, that is 5. Okay, so here my M is equal to 5, so my waiting time is equal to 5. So again I have to calculate the number of required buses, that is for the first bus I have 1 and waiting time is 1 minus 1 is 0, this is less than waiting time. Again in my second bus 3 and 4 minus 3 is 1, and this waiting time is less than 5. And again I am placing 10 and 14 into the last bus, and that 14 minus 10 is 4, and 4 is less than 5. And after that I just exit the loop, and while exiting this loop I just found my required buses, that is 3, and this is equal to the M. okay, and if my required bus is equal to the m, then I just return false and update my r. And after that I have my l equal to what, 3, and my r equal to 5. Okay, so again I have to find m, that is 3 plus 5 divided by 2, that is the 8 divided by 2, that is the 4. At this time, what is my waiting time? Waiting time is 4. Okay, and again we have to calculate the number of required buses. So in my first bus, that is 1 minus 1 is 0, this satisfy. Okay, in my second bus, 4 minus 3, that is 1, so again this satisfy. And in the last bus, 10 and 14, 14 minus 10, that is 4, this again satisfy, which is less than equal to the waiting time. So after exiting this while loop, I have my required buses. I have my required buses which is equal to the 3. Okay, and at this time, this is again it is equal to the m. Again, if it is equal to the m, so I have to return the false. While I am returning the false, I have to update r equal to m. So at this last time, I have l equal to the 3, and my r would become 4, and I am at my cutoff limits. Okay, and after that, this condition l plus 1 is less than r is failed, so I just exit out from the loop, and after that, and after exiting from this loop, I have my maximum of waiting time. Okay, which is r, which is 4. Okay, now coming to the time complexity, I initialize my l as a 0, r as a arr, I minus arr 0. Okay, so for the time complexity, I have big O of log base to the 2 maximum of arri minus minimum, and this is our overall time complexity, maximum of arri and minimum of arri. And after finding this time complexity of the last question, I am concluding my lecture over here. And in future, whenever you tackle a binary search problem, either it is easy or hard, just apply 4 steps logically and you will conquer any type of question which is related to the binary search problem. And if you like this content and if you want more, please like this video and subscribe to this channel and share among your friends. And if you